Good morning, everyone. On the way in, you should have picked up a transcript that says, "What is science?" It's from a radio clip that we're going to play for you today. So while you are listening to the audio file, it's also linked in Canvas. You can listen to it. There's a transcript, okay? And the transcript goes through, and we're going to ask you to annotate and underline and highlight if you want to highlight. Make notes along the way. Yesterday we talked about hypothesis, theory, laws, facts. Those are kind of the things that are going to be emphasized in this audio clip. So it's about, I think it's like 2 or 3 minutes long. There's a lot of information that is good information. So I'm going to ask you to listen and kind of look, again, looking for those key terms, and we'll talk briefly about the audio file. So that's what you're going to do. If you want a highlighter, there's a few highlighters up there still. When we're done, I'm going to ask that you put them back. So here is the audio file that goes along with the transcript that is in front of you. I think.
It's YSO Science Thursday.
This is Dick Fowler with Science Thursday on WYSO.
Not quite yet.
And we are joined
As soon as the
by
voice
Jeff
changes,
Moore.
then we're reading.
I recently saw an article in the newspaper reporting on more challenges to the state on issues of science education. The reporter did a nice job of explaining what the issue was all about, but at one point she described science as something that proves theories. Ugh, my heart sank when I read that. It was an unfortunate case of a well-intentioned reporter that doesn't understand the process of science very well. Unfortunately, many of us probably think this is what scientists do. So let's roll up our sleeves and get down to work understanding what was wrong with the reporter's statement. So often in life, we use the word theory when we should really be using the word hypothesis. It's unfortunate that this misuse appears all the time in print and over the airwaves, even on our favorite NPR programs. To be sure, a hypothesis is an educated deduction, while a theory is a well-evidenced explanation of why some phenomenon occurs. A scientific law is a related term. It is a well-evidenced description of what happens, not why something happens. To be well-evidenced, scientists usually run countless experiments, or they analyze countless amounts of data relevant to their hypothesis or question. When you think you know who stole your cookies from the cookie jar, you don't have a theory about who took them, you've made a hypothesis about who took them. Now, no matter how much evidence scientists gather, they can never say they have proven something. A scientist is always open to the possibility that some future evidence will show their theory or law is not correct. That's okay. Science is in the business of trying to figure out what really is going on and why. We can only do this by gathering evidence. If some experimentation comes along to cast doubt on a theory or law, then more research will go on until there is a consensus in the scientific community. But even that consensus may change with more evidence. Take, for example, global warming. Almost all scientists are in agreement that global warming is occurring and that human activity is a major cause of this. This statement is supported by careful scrutiny of mounds of evidence. Could scientists be wrong? It's possible. And if future evidence shows that they are, then that is okay, scientifically. However, scientists become more confident of their theories and laws the more that evidence continues to verify original conclusions. To date, evidence continues to be very much in favor of supporting the theories and laws associated with humans being a significant factor in global warming. So back to our well-intentioned newspaper reporter. The reporter's statement that science is in the business of proving theories is off track because science just can't prove anything, and scientists set off searching for patterns from questions or hypotheses, not theories. All scientists can do is say, the evidence supports the hypothesis that. Wow, what a little soapbox session this has been. I have a hypothesis, though, that our time has made us all better at understanding the process of science. But alas, I shall never prove it.
Jeff Bohr is a civil engineer and a physics teacher at Carroll High School.
All right, so give you 30 seconds to kind of go through, find again, so maybe I went a little fast, find some good information, theories, laws, hypothesis, fact, those are the things you're looking for. We'll talk about this in a few, like 30 seconds or so. So I'm going to emphasize a few things that I want to make sure we get emphasized. It talks about how we sometimes, in everyday language, misuse the word theory when it really should be talking about hypothesis, right? We addressed that yesterday. I addressed that yesterday. We talked about that yesterday. We, in everyday language, misuse the term theory when it really should be hypothesis. And that's okay as long as you realize what the context of the word is. Okay, so if you're talking with your friends about who, you have a theory about who got the highest score on a test, okay, fine. Just don't carry that over to science when they talk about theories in science, because if it's a true scientific theory, it has a very different meaning than you in your everyday language. So just be aware of that. Okay, so there's some line numbers. So like here's 15, so 14, 13. So like on line 13, I highlight in blue a hypothesis. It's an educated deduction. Just to reinforce that idea, it's an educated deduction based upon some prior knowledge, not a complete random guess. Okay, there's a difference between a random guess and a hypothesis. A theory is well-evidenced explanation of why. It's the why. It's the why. Theory is a why something occurs. Or a scientific law is a well-evidenced description of what, not why something happens. Okay? It is the what happens. A scientific law describes what. So they use the term well-evidenced, well-evidenced. Here's what well-evidenced means. Countless experiments analyze countless amounts of data that relevant to their hypothesis or question. Countless means lots and lots and lots and lots and lots. It's not me doing a single lab of radish seeds and aspirin in room 221, publishing that paper to the entire scientific community and say, hey, I did this one time in this one room at this one class, and we planted some radish seeds. Here's a scientific theory as to why the aspirin didn't grow. That's not well evidenced. That would be my hypothesis, because I did some experimentation and I might have some data, but there's a completely different level when we talk about well-evidenced versus just everyday stuff. So theory is the why a phenomenon occurs. A law is the what. It's the what occurs. Okay, it's what occurs. Okay, and then that's what well-evidenced means. On line number 21, we never can say that we've proven something. In science, we don't say we've proven something. We say we have evidence that supports, or we have evidence that refutes our original hypothesis, denies, goes against. Okay? So in science, we don't like to use the word prove. Prove is not something we do, because prove means absoluteness. It means I'm right, and nothing ever, ever, ever is going to come along that says otherwise. And that's not what we do in science. That's not what science is. Science is to get to the best explanation we have with the evidence that we have, and with new evidence, we get better understandings. Okay, so we're always open to that new future evidence, and science is in the business trying to figure out what is going on and why. That's the goal of scientists, based on evidence. My wife teaches this year, new this year, 7th grade language arts, okay, at the middle school. And in their language arts class right now, they're doing claim, evidence, and reasoning, CERs, right? And you guys did those. And they are doing exactly that. They're making claims based upon evidence. Now, they aren't talking about scientific claims. They're talking about character development based upon some stories and stuff like that. But the ideas are still true. We make claims based upon evidence. And when we talk about these scientific theories, we want to make sure they are with lots and lots of evidence. Okay? One thing we wrote down at the bottom of our sheet, second hour, which I think is an important thing for you to put in writing, because this is a question we get, too many people get wrong each year when we ask questions about this on the test. It's a common misconception that people have. A theory will never become a law. I would encourage you to write that down. A theory will never become a law. remember, a lot of people have this idea that a theory is a hypothesis, right? That's what they think in their mind. So they're like, well, it's just a theory, it's just a hypothesis, so once they get more evidence, it'll become a law. But a theory and law are two completely separate things. They're both well evidenced, which means they have mounds and mounds of data and evidence to support their claims. But they're two separate things. This theory is the explanation as to why something occurs, whereas a law is what occurs. With more evidence, a theory doesn't become an explanation of what, because a theory was the why or how something happened. A theory will never become a law. Okay, the germ theory is an explanation of why people get sick when germs enter your body, is why you get sick. It's a proposed explanation based upon it was from our video yesterday. But with more data, it's not going to be the what. It's not going to say what is the germ theory, or it's not going to be the, I'm sorry, I said that wrong. It's not an explanation of what occurs, it's an explanation of why things occur. Two separate things. Theory will never become a law. The germ theory will never become the law, the germ law. Okay? On the back, it kind of continues, but we keep going until there's a consensus, and we collect more data until there's a consensus in the scientific community. Consensus means we come to an agreement. Now, it's not always 100% of the scientific community agrees on something. There's data that some people are like, you know, based upon that data, I don't think that's a fair conclusion. But we look at overall, is there a consensus? Is there a, hey, yes, we agree, hey, most of us in this room who are experts in this field agree that this is a valid explanation, then we can come to a consensus that, yes, this is what we think is really going on. Okay? Might there be a person or two in the room that doesn't? Sure. Okay, but generally, big consensus. Careful scrutiny of mounds of evidence. If I had a mound of cash, what does that mean? A lot, right? I have a lot of cash. I have this mound of cash. I have a big pile of cash. I don't. Wish I did. Same thing when we talk about mounds of evidence. A lot, a pile of evidence. Lots and lots and lots. It's okay to be wrong. Okay? It's okay that their original predictions are wrong, or a theory that we thought was true for 200 years. If new evidence comes along and says, hey, you know what? That isn't really how it works. That's okay. That's okay. Okay? However, with more confidence in their theories, when we get more and more data, the more evidence we have, the more confident we are in those conclusions that they draw. And that's the basis of the scientific process. Okay? And the last thing I went through and I thought was important is, in science, all we can do is evidence supports the hypothesis step. We can't say we prove, we can say we have evidence that supports, we have evidence that refutes, or we have evidence that disproves. I don't know, I'm always a little leery to use disproves because I say we can't use proves, so I don't know if disprove, I'm always a little torn on that one. Because it's like absoluteness, and science isn't about absolutes. Okay? So those are some things to think about. Theories, laws, hypotheses. On the board, we have these also kind of written down again, just to kind of re-emphasize. You will take your test next week, Wednesday. Tomorrow in class, we are going to take a practice test. Okay, we'll do a practice test tomorrow in class. This actually, I know there's a thing for you to submit in Canvas for this. There was a set of questions. I'm not going to do the questions anymore, so there is no submission in here in Canvas. So sorry about that. There originally were like 6 questions I was going to have you answer, but I decided talking through it was maybe better than having you answer those questions. So don't worry about submitting anything in Canvas for this one, but I appreciate that. I saw a couple of you were about to do that. So if you did, whatever, don't worry about it. We'll do a practice test tomorrow in class. On Monday, Tuesday, we're going to start talking about properties of water, which will not be on Wednesday's test, but it'll give you an opportunity It's like stations, we're gonna go through and look at different properties of water and how it behaves. We're gonna talk a little bit about water in terms of chemical behaviors, and then on Wednesday, we'll take our test. Okay. I have a 5-minute video I wanna show you quick as well. And then we're gonna go through an example or two and give you some work time on a different worksheet. The video I'm about to show you is by Neil deGrasse Tyson. I don't know if you know Neil deGrasse Tyson. He's kind of been a science education spokesperson in the United States. I'd say over the last decade or so, I've seen more and more of Neil deGrasse Tyson. He is the narrator in the Cosmos series, the newer Cosmos series. That's Neil deGrasse Tyson. He's an astrophysicist. He's a pretty smart guy, and he does a really good job of explaining things. Complex ideas in understandable terms. So this video was published back in, well, this video was posted on YouTube back in 2017. It's not new. It's not about COVID. It talks about what science is. Okay, and science in America and how we should make decisions in America based upon science. So we'll watch this video. It's 4.5 minutes long, and then we'll go through an example on a different worksheet. So.
How did America rise up from a backwoods country to be one of the greatest nations the world has ever known? We pioneered industries. And all of this required the greatest innovations in science and technology in the world. And so, science is a fundamental part of the country that we are. But in this, the 21st century, when it comes time to make decisions about science, it seems to me people have lost the ability to judge what is true and what is not. What is reliable, what is not reliable. What should you believe, what should you not believe? And when you have people who don't know much about science, standing in denial of it, and rising to power, that is a recipe for the complete dismantling of our informed democracy.
Let us demand that educators around America teach evolution not as fact, but as theory.
Increasing number of parents showing skepticism about vaccinations.
Voters have approved a ban on GMOs.
Call climate change unproven science.
That's not the country I remember growing up in. Not that we didn't have challenges. I'm old enough to remember the 60s and the 70s. We had a hot war and a cold war, a civil rights movement, and all of this was going on. But I don't remember any time where people were standing in denial of what science was. One of the great things about science is that it is an entire exercise in finding what is true. An hypothesis, you test it. I get a result. A rival of mine double checks it because they think I might be wrong. They perform an even better experiment than I did and they find out, hey, this experiment matches. Oh my gosh, we're onto something here. And out of this rises a new emergent truth. It does it better than anything else we have ever come up with as human beings. This is science. It's not something to toy with. It's not something to say, I choose not to believe E equals MC squared. You don't have that option. When you have an established scientific emergent truth, it is true whether or not you believe in it. And the sooner you understand that, the faster we can get on with the political conversations about how to solve the problems that face us. So once you understand that humans are warming the planet, you can then have a political conversation about that. You can say, well, are there carbon credits? Do we do this? Do we put a tariff on it? Do we fund? Do we subsidize? Those have political answers. And every minute one is in denial. You are delaying the political solution that should have been established years ago. As a voter, as a citizen, scientific issues will come before you. And isn't it worth it to say, all right, let me at least become scientifically literate so that I can think about these issues and act intelligently upon them. Recognize what science is and allow it to be what it can and should be in the service of civilization. It's in our hands.
Okay, so I think I used the term emergent truth the other day, but the point that Neil's saying, or what he's saying, I don't know why I'm calling him Neil, it's not like I know Neil, whatever, Neil, the buddy, you know, we should be making decisions based upon evidence, because that's what science is. And let's make sure that when we talk about science, we're talking about what the science is, not the politics of what we're saying it is or isn't. Okay, so that's the idea of this, and we're going to kind of transition. The next thing, there is a packet that I'm going to ask you to pick up. If you are done with the highlighter, now you maybe want to do a little bit of highlighting quick on the other, you can put them back in that thing. There's going to be two stacks of these. There's a stack here, or there's a stack up on the front part. Grab one of them. They're the exact same thing. You need a copy of this packet that we're going to go through next. Again, if you want to turn in your highlighters, fine. If you want to use it for the top, because there's a little bit we could use from. You could use it for, that is up to you. All right, a big part of this unit is setting up good experiments, a valid experiment. In order to set up a valid experiment, there's certain things that we have to have in place. We have to have one independent variable. We have to have as many standardized or controlled variables as possible. Okay, and that's what this is kind of a practice and for you to help identify that, because these are things we think are important and that you'll be asked on your test to identify. So, again, I went through, since I had a highlighters in my hand, I went through and said, hey, what is the independent variable? The independent variable causes the change, or it's the thing that I change. That's the way I often think about it. I take the first person approach and say, I am the experimenter. What did I change in this experiment? That's our independent variable. It's the cause. Or my dependent variable is the effect, or it's what are we measuring? Because I changed this, what effect did it have on the dependent variable? Because I added aspirin to my bags, what effect did it have on the germination of the radish seeds? And when we go through and we identify these, I think it sometimes helps to identify the dependent variable first. What are we measuring? What are we looking at? And then we can say, well, what did we change and we're looking for? All other things must be standardized, or we can say they're control variable. We got to keep them constant throughout this, because that could change your results. And in a valid scientific experiment, we can only have one independent variable. If you have two independent variables, it's an invalid experiment. Zero conclusions can then be drawn. You can have one and only one. So, an example of this is Mrs. Took wants her students to see how much time it would take for paint to mix in different water temperatures. Okay, so we went through and she underlined some things. Those are the two variables. That's in your instructions. It'll be below. But we're supposed to underline our two variables and then come up with what is the independent, dependent, and some standardized variables. So if Mrs. Took wanted to see how much time it would take for her paint to mix, what did I, taking the first person approach, pretend like I'm Mrs. Took for a second, what did I change in the experiment? Well, I changed the temperatures of the water temperatures. Right? That's what Mrs. Took changed. What is she measuring? And this should be actually a little bit more descriptive. Instead of simply just saying like it's the time to mix That's what she's going to measure. How much time does it take to mix this paint up? I'm changing the temperatures. I'm going to measure the amount of time it takes to mix paint. If we say that might have some impact on an experiment, then we need to standardize it. We need to have it be controlled. So if we were to say, well, if I vary the amount of water, that might affect the amount of time. Well, then we got to keep it the same. If we say, well, what if we use different amounts of paint? Well, that's going to have an impact. Then we got to keep it the same. If we change the types of paint, we got to keep it the same. So 3 things that she would have to standardize is the amount of water, the amount of paint, and the type of paint she used. Okay, so the first one we'll go through together. The directions say, for each of the following experiments, underline the 2 variables in the sentence and identify what's the independent, dependent, and list at least 2 standardized variables. Okay, so Austin wanted to find out what would happen to the temperature of tiny marbles if we shook them for different, in a container for different amounts of time. The 2 variables I underline. It's the temperature of the marbles and the different amounts of time. Now let's pretend I'm Austin, or you pretend that you are Austin. What am I, Austin, what am I going to change in the experiment? Am I changing the temperature of the marbles, or am I changing the different types, amounts of time?
Amounts of time.
I'm changing the amounts of time. And what are we measuring? Because I changed the amounts of time, I am measuring the temperature of those marbles. Okay? So I'm changing the amount of time that I shake them. I'm measuring the temperature of those marbles. Cause and effect. What did I change? Independent variable. What are we measuring? That's the dependent variable. Now my second hour brainstormed some ideas for standardized variables, which may or may not match what you're about to tell me. But a standardized variable we think could have some impact on the experiment, so we must keep it the exact same in all of my trials. What's something that might affect the amount of the temperature of the marbles?
Maybe like the temperature of like the room or like the place you're in.
Okay, so maybe the starting temperature of the room that those marbles are at. Okay, so we should start it always at the same temperature. What else?
The container.
The container, right? We should use the same container. What else? Yeah.
The same type of marbles.
The same type of marbles. Let's keep on that. The same number of marbles. Or we could even go and say, let's use the same marbles, right? So there's lots of different things. The same amount of shaking. The same, how hard we shake them. I don't know exactly how we would word that. Okay? You're only going to need 2, but realize there's lots of them. The more things you keep constant, the better your data should be, the better conclusions we can have, because then you only have 1 independent variable. If we were to change the number of marbles, is that a valid experiment? No, because we changed the number of marbles between the 2 jars, and we changed the amount of time we shook it. I have 2 independent variables. No conclusion can be drawn from that statement. So, with that, there's some practice for you. Mr. DeBoer and I decided second period that there are 16 of these, and that gets to be a bit more than we probably need. So Mr. DeBoer and I decided that on page 2 are questions 2 through 6. And we're saying questions 2 through 6 is a sufficient amount of practice that we feel most of you need. So that's what we're going to ask you to turn into Canvas, is page number 2. You only have to give us page number 2 because we went through page number 1 together. Okay, there's 4 questions on page number 2. If you say, hey, I could really use some additional help, go ahead. There's 2 more pages of them. But at some point it becomes kind of pattern recognition, and you should get pretty good with them after a while. But we think probably 4 additional on your own is sufficient. So when you turn this into Canvas, and we have some time today to get this done before you walk out of here probably, you only have to turn in page 2, which has questions 2 through 6. If you want some additional questions to practice, there they are. If at any point during these you say, hey, how what would be a standardized variable on this? Let me know, and I'll be happy to help you with this. Or you say, did I get the right independent variable? Is this right? Let me know, or talk to a neighbor, and we can kind of work through it together. Let me know what I can do to help.